All right, y'all, so this is the example we're going to look at right now. It's a mass that is on a ramp, and we're going to look at, we're going to try to find its acceleration. We're going to find out what its speed would be at the bottom of the ramp with that acceleration, and then we're also going to determine how much friction there should be. So you'll notice that friction is one of our new ideas, and we're going to be connecting it to this thing that we've already done before. So without further ado, let's go ahead and see what we can do with this question. So let's go. All right, let's go. So we've got this idea of the block that has a mass of 2 kilograms. They did give us the angle of 30 degrees, and that's it. So at this point, you have to decide, well, I know two different things that work with acceleration, right? We've got our Suvat equations, our kinematics. In order to do that, I need to have displacement, initial velocity, final velocity, acceleration, and time. I need at least 3 of those, and then I should be able to find the other 2. That's how the Suvat equations work. They all have 4 things. You need 3 to find the 4th, all right? And you can always use that with a different equation to find the 5th. So let's see what we got. Well, we do know that I guess we could assume it starts at rest, right? So we could assume that it starts at rest. Other than that, I mean, I don't know. I guess we know the height, so maybe we could use that to find the length, the distance, so initial velocity and distance. Unfortunately, I don't have anything else. At this point, I don't know its acceleration. I don't know the time that it's going, and I don't know its final velocity. So with all those unknowns, Suvat kinematics seems like it's probably not the best way to go about this. I can also get acceleration from the sum of the forces, right? Sum of the forces equals ma. And so that's what I'm going to try to do here. I'm going to try to go sum of the forces equals ma, because I do have the mass. So if I can find the sum of the forces, then I should be able to put those things together to be able to find the acceleration. So we're going to start by doing a free body diagram. Okay, so we're going to have the force of gravity, which is down, and then we'll have the normal force, which is of course normal, perpendicular to the surface. Okay, now one of the things that we learned in class is that when we have something on a ramp, that it's a good idea to tilt our axis. So instead of having our x and y be this way, we're going to tilt our heads a little bit, and we're going to look at it now in this direction so that my x-axis is parallel to the slope and my y-axis is perpendicular to the slope. Now, if the y-axis is perpendicular to the slope, then that means that the normal force is going to be 100% perpendicular. The force of gravity is going to have a horizontal component and a vertical component, and that's actually going to be really, really important as I go forward. So my next step here, I can get the force of gravity, right? I know that the force of gravity is equal to mg. So if the force of gravity is mg and I've got the mass, then I can just go the force of gravity is equal to 2.0 times g, which is 9.8, and I can get that the force of gravity is 19.6 newtons. Now, if this were my final answer, because my mass was only 2 digits and my 9.8 was only 2 digits, then I would actually write my answer in only 2 digits. But because this is an intermediate step, I want to keep all the numbers there. So I'm going to go ahead and keep the 19.6. We'll keep going with that. So I know the force of gravity. We're going to now, remember we talked about in class that if the ramp has an angle of 30 degrees, then this angle right here is also 30 degrees. Why? Because the y-axis used to be straight down, and as we take the x-axis, which was horizontal, and tilt it this way, right? Here's my y-axis, so as I tilt the x-axis this way, you'll notice that the y-axis, which was straight up, is being tilted over in that direction the same degrees. So whatever I do with my x-axis rotating up that way, the y-axis rotates over exactly the same amount, so 30 degrees. And so that then allows me to find the horizontal component of gravity and the vertical component of gravity. And remember, these horizontal and vertical are with respect to my new horizontal and vertical. So the horizontal piece is opposite the angle. So that's going to be the sine. So I'm going to go sine of theta equals opposite, which would be FG horizontal x over FG. And then I can multiply both sides by FG. And so my FG is 19.6. So I just go 19.6 times the sine of my angle, which was 30 degrees. And I get 9.8. So that means FGX is 9.8. And I'm also going to go ahead and find the vertical component here because I am going to need that later. And so that's the adjacent side. So I'm going to do cosine of theta. That would be adjacent over hypotenuse equals FGY over the hypotenuse, which is FG. So again, FG is that 19.6. So I'll go 19.6 times this time the cosine of 30, which will give me 16.97. So this will then be the FGY equals 16.97 newtons. All right, so I'm going to use both of those here in a little bit, but let's go ahead and first do this one, right? If we're looking at my forces here, the block is only sliding horizontally. It's only going along my x-axis, which means that the y forces must balance, right? I just found the y component of gravity, which was 16.97. That must mean that the normal force is also 16.97, right? That will also, both of those vertical forces, because the block isn't going vertically, it's only going horizontally along the x-axis. And so therefore, the only force that is not balanced is that horizontal force, that horizontal component of gravity. So when I do my sum of the forces equals ma, the only unbalanced force is FGX. So I'm going to go 9.8. Now remember, that's 9.8 because that's the horizontal component of the force. That's not 9.8 because little g is 9.8 meters per second squared. That's just a coincidence that that ended up being the right value. Okay, equals the mass, which is 2, times the acceleration. And so now I can take that 9.8 and I divide by 2 and I get 4.9. So I get that the acceleration equals 4.9 meters per second squared. All right. Now, that's actually the answer to letter A. We just did sum of the forces equals ma. We got the acceleration. Now, in context, that should kind of make sense. It's not 9.8 because it's not going to accelerate as fast as it would if I just dropped it, right? It's going to have a little different acceleration because it's going down the ramp. It'll be a little bit slower, right? It'll speed up at a slower rate. That's what acceleration is. And so 4.9 meters per second squared, we'll take that. That's fine. Letter B says if the block starts at the top of the ramp and the ramp is 1 meter tall, what speed will it have at the bottom? Okay, well, if we take the ramp, which we know is 30 degrees, and it's 1 meter tall, then we should now be able to use our acceleration. This is what's happening, right? It's starting up at the top, and it's going down the ramp in this direction. We know the acceleration for that time. The acceleration is 4.9. We can go ahead and assume that it's starting at rest, 0 meters per second. Now, because this is 1, the height is 1, I can find the length of the ramp, right? So you can use trig to do that. Hopefully you got opposite and hypotenuse. And you go through, you say sine of 30 equals opposite over hypotenuse, and hopefully you end up getting 2 meters there being the length of the ramp. And so we now have a displacement, which is 2 meters from there to there. We have our initial velocity, we have the acceleration, and we are looking for the final velocity. We don't have time. We don't need time, right? So we're going to leave time out of it. We're going to use the equation v squared equals u squared plus 2as. And that should then allow us to solve for the final velocity at the bottom of the ramp, which is what speed it has at the bottom of the ramp. So the u is 0, so 0 squared is 0. We can leave that alone. So we'll go v squared equals 2 times the acceleration, which is that 4.9, and then times the distance or displacement over which it travels, which is again another 2 meters. And so 2 times 4.9 times 2, which is 19.6. And if I square root the 19.6, I get 4.4271. All right, so my V is going to be 4.4 meters per second. All right, there we go. So this is a nice question. It caused us to use our idea of forces. It caused us to use the idea of vectors and components. It caused us to use the idea of kinematics with our suvat, right? Lots of stuff going on here. The final question is this. What is the minimum coefficient of friction required to stop the block from sliding? All right? Now, if we go back to our original picture, right? We look back at our free body diagram from before. The vertical force is already balanced. So friction, what does friction need to do? Friction needs to oppose that horizontal component of gravity. So therefore, friction needs to be in this direction, and we know its magnitude. We know how much friction there needs to be because we found that the horizontal component of gravity was 9.8 newtons. That was how much force was in this direction. The component of friction must be the same, right? So now we're using Newton's laws to be able to figure out, well, in order for the object to stay at rest, the forces must be balanced. That's Newton's first law, right? If the forces are balanced, it'll maintain its state of motion. Okay? The question could have just said, what is the minimum coefficient of friction required so that the block slides at a constant velocity? Right? That would be the same thing. If it's a constant velocity, the forces must be balanced. In any direction, whatever we need, we got 9.8 newtons. Now, the question is not how much friction should there be. The question is, what is the minimum coefficient of friction? So in your reading or in class, we learned that the force of friction is equal to the coefficient of friction times the normal force. Now, technically, what type of friction is this? Well, if it's at rest and staying at rest, then the type of friction would be the static friction, right? That's the friction when an object is at rest, but it's trying to slide, it's trying to move, but friction is opposing that attempt. That would be static friction, all right? So it is going to be static friction. We know that the value of the friction must be at least 9.8. That's what we just found there. So I'm going to put 9.8 there. I'm looking for the coefficient of friction. And the normal force, I told you I was going to use this later. We did find the normal force earlier. It was 16.97. Okay? And so with that, we can take the 9.8. We can divide by the 16.97. And we get 0.577. And so I'm going to say the coefficient of friction is 0.58. The coefficient of friction does not have units. Okay, you may think that's a little weird, but recognize that this is in newtons. This is also in newtons. Therefore, the only way that these can both be newtons is if this doesn't have any units at all. It's just a ratio. It's a ratio of how much friction there will be dependent on how much normal force there is between the two surfaces. All right? Now, the reason why the question says the minimum coefficient of friction is because if this is the coefficient of friction, then I will have this much friction, okay? If the coefficient of friction is greater for static friction, then this number has the capability of being higher, right? It could be more. Now, in this situation, it would still be 9.8, because if it was bigger, then it would be bigger than the force of gravity down the hill, and it would start going up the hill. Static friction is a little bit weird, though, is that static friction has a maximum value. The value that it will have is the value that is necessary to keep the object at rest. All right, and we'll talk about that hopefully more in class. You can ask questions about that in class if you would like. But the point here is that this is the minimum. That's the least coefficient of friction possible. If it was bigger, there would be more friction available, but the friction that would be there right now is still 9.8 newtons. All right, so we've been able to answer all the parts of that example question. I promised my students that I'd add a little bit here at the end. So what I'm adding here is this question right here. All right, which is a question with a piano and a girl pulling over on the end. All right, and the question was, how much force does she need to exert? Well, if you treat the piano and the pulley and the rope inside as a system, as a single object, then what you end up seeing is that gravity's pulling down on that. And then there are two tensions pulling up. Yes, it's the same rope, but the rope is pulling up here and the rope is pulling up there. So you actually have tension twice. Now, if you do have tension twice here, then that means that the force of gravity must be equal to 2t. And so I solve for that here. That gives me that t is 500 newtons. Now, when you go over to the girl here, you notice that there is only one t there. That's the force that she has to exert. So she has to exert a tension of 500 newtons, and that's it. This is an interesting concept, because what it means is if I had a system of pulleys and I added more pulleys and more pulleys and more pulleys, that what that would mean is that I can decrease the amount of force that this person must be exerting. That force would be distributed over each of those ropes and each of those pulleys, and it would make it much, much, much easier to pull the piano up. Now, I've actually used this in real life before. I used to be in Boy Scouts, and we would go whitewater canoeing. And in those when we went whitewater canoeing, the rapids, sometimes the water would be very, very strong. And so we were taught that if the canoe ever got pinned up against a rock and we could not move the canoe, that the way that we could remove the canoe is by tying a rope to the front and then going over a series of pulleys, which we would then attach to a tree, and then we could pull on it. The more pulleys that we included, the less the force was required for us. We could exert the same amount of force, but it would have a much larger effect then on the canoe itself. So it's kind of cool the way that you can use pulleys to distribute force and to allow you to have multiple tensions pulling on that object, and yet the person exerting the force does much less. Now, there is a cost. Each distance, the distance that you pull will end up being greater. Because if I pull it a meter and I have 5 different strings, each one of those strings is only going to go 20 centimeters. And so there is a cost. It's not free energy. It's not free force. There is a cost, but it is helpful in allowing you to apparently increase the force available. All right? So that's the end of our example and our little concept test there. I hope that was helpful, and I'll see you next time.